a second.
Sure.
Okay, we are live.
Fantastic, thank you. So welcome everyone to this UniKORN Frontier seminar. And today we're really excited to have Dr. Marko Toroš join us. And Marko is a research fellow at UCL who's working on quantum mechanics and the interface between gravity and quantum mechanics, and also phenomenology with optomechanical systems. So thank you so much for joining us today, Marko, and please take it away.
For inviting me. Hello, everyone. Can you see my presentation?
Yes,
Hello?
that's all good.
Oh, great. So first of all, Sophia, thank you very much for inviting me. And also thank to everyone that has come to listen to my presentation today. So today I will talk about 3D coherent scattering in levitated optomechanics. So let me give you just briefly the outline of the presentation. So I will just, in the first part, I will just briefly discuss a little bit on what I've been working in the past and what I'm currently working. Then the main part of the presentation will be on the 3D coherent scattering setup, in particular about hybridization effects. And then at the very end, just two small slides, I will discuss a little bit about why 3D coherent scattering is important and how it could be used in the future to test gravitational effects. And I will clarify what I mean by that in the following. So so let me briefly introduce myself for to those that don't know me. So I come from Slovenia. So this is right next to Austria, Italy, Hungary, and Croatia. So this is a picture of the Julian Alps, which is about these are mountain peaks about 2,000 meters high. And this picture was taken about 1,600. I remember the day, so it was the 1st of January 2018. Of course, today there is no snow. So if you have a chance to visit Slovenia, it's a very beautiful country, full of nature. So ideal for hiking or small walks, or just enjoying a little bit of silence. So let me tell you a little bit about my academic path. So I did my PhD in the University of Trieste. Then I did my first postdoc at Southampton University. And I'm currently now working at University College London. My work has been split mainly between two things, I would say. So on one hand, phenomenology, on the other hand, more abstract theory. On the phenomenology part, I've started working first on matter wave interferometry, so buckyballs, large macromolecules. Then when I moved to Southampton, I started working on levitated optomechanics. Here I just maybe want to mention one interesting result. So together with Dasser, Ashley, and Professor Henrik Ulbricht, we have seen precession motion. So when a particle is not symmetric, it can spin, rotate in very different complicated ways. And after that, but still working at Southampton, I started working also a little bit on photon interferometry. And when I have then moved to UCL, I'm mainly working on cavity optomechanics. In parallel, I have initially worked a little bit on foundations of quantum mechanics or collapse models. I have become quite interested also on possible experiments to test the nature of gravity. And I'm also very interested also what happens to quantum states together with non-inertial motion. So I want just to briefly mention two papers that have been done jointly with a research group in Glasgow. So the idea is essentially take a quantum mechanical system, place it on a table, and spin the table. The question is what happens? What we have found is that even at very low rotational speeds, the interplay between quantum mechanics and relativity leads to quite some remarkable consequences. in other words, here one is testing together quantum mechanics and relativity in a non-inertial regime. Let me now move to my current, let's say, main occupation. So today I will talk with a joint work with Professor Tania Monteiro about 3D coherent scattering. I'm also working quite closely with Professor Sugato Bose and Professor Peter Barker. So let me just mention one paper. So we have recently put it on archive. The idea is how, so the goal in this paper, we ask the question how to create a superposition for a large nanoparticle, a massive nanoparticle, or even a microsphere. The idea is very simple. So you place first the nanoparticle in a Paul trap, you then illuminate it with an optical field, you trap an atom near the nanoparticle, and which couples the atom and the nanoparticle. If now one moves the atom using lasers, also the nanoparticle will move. And if one creates a superposition, spatial superposition for the atom, also the nanoparticle will be put in a spatial superposition. So this is just, I wanted just to give you like a very brief introduction on what I have been doing and what I'm currently doing. But now let me start with the main part of the presentation. So today I want to talk about 3D coherent scattering. I would say 3D coherent scattering started so quite unexpectedly, at least for me. So in 2018, maybe late 2018, this led to two papers that were published in March 2019. I will particularly talk about an experiment that has been done in the group of Professor Markus Aspelmeyer, who gave a very nice talk last week. Let me start by very briefly discussing the experiment. So here, if you see my cursor, one has a tweezer that illuminates a nanoparticle. The nanoparticle then scatters inside the cavity. So one obtains a coupling between the tweezer, the nanoparticle, and the cavity field. This is sort of a viewpoint from the side. You can see that if you move around the tweezer with respect to the cavity, you can move the nanoparticle, let's say, from the antinode to the node or to any other position. So it's quite versatile. Viewed the same experiment, let's say, from the top, there is another important parameter, which is, here I'm considering linearly polarized light, which is the angle between the polarization of the tweezer light here along the y-axis and the cavity axis. So this angle, I will call it theta. So let me just repeat, because this will be playing a bit, these two parameters will be critical. So one is the displacement of the particle with respect to the cavity node. The other one is the angle between the polarization of the tweezer and the cavity symmetry axis. So together with Professor Tania Monteiro, we have studied this system theoretically. So I wrote down the Hamiltonian. So we introduced a cavity field and a tweezer field. By then essentially carrying out the calculation, one finds an explicit expression. Here you see this phi, which this will be the displacement from the cavity antinode of the particle or the tweezer center. And you see also the angle theta, which is the angle between the tweezer polarization and the cavity symmetry axis. Further expanding this expression to quadratic orders, one finds just 6 terms. So let me briefly discuss this term. So we have the coupling of the mechanical position x to the cavity amplitude y. This is what is usually discussed in all optomechanics, cavity optomechanics textbooks. Then you have also a coupling of y to the cavity amplitude. This is not particularly surprising given the symmetries of the setup. And then there's the first surprise. So the z position is coupled to the phase quadrature of light. This I will call indirect cavity-mediated couplings. So essentially, cavity here plays a dynamic role for y and p, two quadratures. In addition, there are also 3 new couplings which couple 2 mechanicals degree directly. So for example, this coupling couples X and Y 2 mechanicals degree directly. One can think about this coupling in some sense as the Coulomb interaction. So also there, the electromagnetic field does not play a dynamical role, but nonetheless, the coupling is there. Also here, if one switches off the optical field, also this coupling disappears. So one can think that these couplings are induced by the optical field, but the dynamics of the optical field does not play any role in the description. Let me then ask, we have then asked what happens to the dynamics. So when you solve the dynamics, what happens? The full dynamics, say for the X motion, here 3D stands that we are considering the full 3D problem, has 2 contributions. So it has 1 contribution, which would appear already by treating a single mechanical degree of freedom coupled to the cavity mode, completely ignoring all the other mechanical degrees of freedom. In addition, there are 2 new couplings. These are essentially the coupling of the Y and the Z motion, either through direct coupling or indirect cavity-mediated coupling to the X motion. One can find very neat expressions for this 3D coupling, these curly G's. Essentially, it depends on the direct couplings, but also on the indirect cavity-mediated couplings. The other quantities are susceptibilities. Let me, without going too much into detail, give you a more concrete example. So suppose the Z motion has a different frequency, so it can be effectively decoupled. So the X motion will now have just 2 contributions. The one that would be there even if the Y motion would be absent, plus the correction due to the Y motion. This 3D coupling can be written in a very simple way. So in this way here, by exploiting a very neat relation between the direct couplings and the indirect cavity-mediated ones. In particular, the 3D coupling essentially depends on the cavity-mediated couplings, on the detuning, the cavity decay rate, and then there is this last factor, 1 minus cotangent square of phi. Interestingly, this term can go to 0. So if you set phi equal to pi over 4, this 3D coupling vanishes. So this last term after the plus vanishes, and on the 3D dynamics reduces to the 1D dynamics. This already is in some sense quite remarkable, because you have 2 mechanical degrees of freedom coupled to the cavity mode, but they are not aware of each other. Let me also show you graphically. So in the regime of the direct XY coupling, so here we're close to the cavity antinode, the cavity does not play a dynamical role, but the Y and X motions are strongly hybridized. Particularly, you can see that the Y has now 2 peaks, one peak at the tweezer Y frequency and a second peak, quite large, at the frequency of the X motion, and vice versa. Also, X has now 2 peaks. Then in the intermediate, in the middle panel, this is the regime of the XY coupling cancellation. So phi is pi over 4. You see that Y is essentially a single peak. There is just a tiny little bump due to X. And also X shows a nice single peak. And then there's the regime of the indirect XY coupling. Here, both the cavity-mediated coupling GX and GY are important. And they couple the 2 indirectly, the 2 motion, X and Y. So you see Y has 2 peaks, and also X has 2 peaks. So this was more or less a very brief introduction to the theory. I'm very happy to discuss in more detail. Maybe you can contact me in the email. I will leave a contact at the end. But let me make the story more interesting now. So most of you have probably been at this conference, but for those that were not there, let me just show you a picture. So this was a conference last year, so end of July 2019 in Bad Honnef in Germany. This was a group photo, and I think I'm somewhere here, but there are also many other people from the community. why I'm telling you this? Because there at this conference, a very special announcement has been made by Professor Markus Aspelmeyer. So this is the actual picture I took at that instant when he, for the first time, publicly announced that the motional ground state has been reached in their experimental setup. This has later led to a paper published in 2020. And in particular, I'm very grateful to Uroš Delić, who helped me a lot to understand their system. So together with Tanya, with the help of Uroš, we tried to model the dynamics inside the 3D coherent scattering setup. And here I want just to mention two of the interesting things. So one thing is the modification of the optical spring effect. So in the first two panels, you see the power spectral density for X, and in the blue one, and in the green one, you see the power spectral density for Y. So you see Y motion has a single peak that does not move around a lot in frequency as you change the detuning delta. On the other hand, the X motion has now two peaks. One peak at the frequency of where you would expect X to be, and one peak at the frequency of Y. So you see here it's about 275, also Y is at 275. Now the actual position, the precise position of the X peak can be calculated using the full 3D theory quite well. It gives rise to an optical spring effect, but it's not just the 1D optical spring effect, so one that would arise by doing an analysis by considering a single mechanical degree of freedom, but by considering both X and Y coupled to the optical mode. So here you see that as you change the tuning, this peak moves and then reappears over there. In this last panel, we have investigated also the optomechanical cooling, which I will now discuss in the next slide. So if one does a 1D analysis, so what is the difference between a 1D analysis and a 3D analysis? Let me first focus on the X motion, so on the blue lines. The blue dashed line is the 1D analysis, so is the phonon number which you obtain by doing a simple 1D analysis. And the solid blue line, there's also a dashed red line just on top of it, is a bit different. So here, physically, it's not very complicated to understand what happens. So the X motion and the Y motions are coupled, and essentially the noise from Y starts hitting also the motion at the X motion. So you have essentially the 1D contribution, this would be the dashed blue line, plus an additional contribution which hits a little bit the system, but not too much. More interesting, and of course, this expression, the red one, is the simple analytical expression we have obtained. More interesting is what happens to the Y motion. You have again the green dashed line is the 1D, what you would find from a 1D analysis. And then the solid green line is what you find from the full 3D problem. And on top of it, you see this dashed red line, which is what you find from doing the actual simple calculation. So you see that it is essentially what you find in a 1D analysis, but rescaled. Interestingly, there is a region, so at a certain detuning, where the 1D analysis would be at a higher temperature than the 3D analysis. So how to understand this? So if you have a noise acting on the Y motion, this could interfere destructively with itself, lowering the temperature. This can be seen from this simple expression which we have derived. So in particular, this N, an absolute value square at the bottom, it's written here at the bottom of the page. And you can read it, you can read this expression like this. So the noise acting on the Y motion through the cavity field is imprinted on the X motion. Then the noise from the X motion again through the cavity field, ends up again in the Y motion, where it interferes destructively with itself. The net result is a significant significant cooling of the Y motion. So here, this essentially concludes, let's say, the main part of the presentation. So I wanted just to show you the importance of the 3D analysis, and then I discussed hybridization. I've discussed optical spring effect and the modification of the cooling rate. Let me now discuss how this system could be used and why this system is very important in my opinion. So it could be used to investigate the interface between quantum mechanics and gravity. Probably the most famous experiment where gravity and quantum mechanics have been tested together is the hauserVerner experiment. This has been done using neutrons. So a neutron is follows two different paths, and due to the gravitational field, it accumulates a non-trivial phase difference. Think about now a nanoparticle trapped and cooled to the motional ground state. You would place it at point A, and then you would put it in a superposition. Why is this important? Because a nanoparticle with respect to a neutron is 10 orders of magnitude heavier. Although no one would be really expecting a deviation from the predictions, I think these experiments are very important to do because nature at the end could still surprise us. Something different might happen which would not be in accordance with the current theories. Let me go even further. So one could also consider two particles cooled to the motional ground state. Then each particle will be put in a superposition. The two superpositions would be separate enough so that no interaction other than the gravitational one would be able to connect the two particles. So essentially the only channel through which the two particles can interact is the gravitational one. This can be accomplished by a careful placement of the two particles that are far enough so that, for example, the electromagnetic interaction is strongly suppressed, but close enough so that the gravitational interaction is not too weak. So this is why it is important to have very heavy particles, because the gravitational interaction is very weak. So nanoparticles, about 10 to the minus 17 kilograms, are very close to what has been proposed. So 10 to the minus 14, maybe even 10 to the minus 15 kilograms. The importance of this experiment would be the following. If entanglement between the two particles would be detected at the end, since they interacted only for the gravitational field would be, one would need to conclude it's quantum mechanical, as no classical interaction can mediate entanglement. So I hope, so this was sort of a probably a very long-term project, but hopefully in our lifetime this will be accomplished. So let me now just summarize the presentation. So I have mainly discussed 3D coherent scattering and hybridization effects. And at the very end, I have given you a brief outlook of why the system could be used. So to test, in particular, to test the interface between quantum mechanics and gravity. So of course, this was a very informal, brief presentation, but I would be extremely happy to discuss these things. So please do not hesitate to contact me at this email. So thank you.
Thank you very much, Marko. And if everyone could just unmute yourself for 1 second and give Marko a bit of an applause. So thank you so much, Marko. Well done. All right, so if there are any questions, please click the raised hand button and we'll be able to pass them to you. I think we have about 10 minutes for 5-10 minutes for questions. I can go ahead and ask one in the meantime. So it's really interesting that you've been looking at this 3D the 3D effects on scattering and on the coupling. So I was wondering is there a reason that this hasn't been considered before? Or have people seen these effects in experiments, but they maybe didn't know where they came from?
So of course, there are 3D couplings in every real experiment, I would say. Of course, so in many cases, the analysis can be decoupled effectively to a one-dimensional problem. But in this 3D coherent, the 3D coherent scattering setup, as the name suggests, as the name suggests, it is really a 3D system in a very in a very important way, in the sense the couplings between the three axes can be very large. So, of course, in other optomechanical systems, there are situations where, for example, when you would have large oscillations, there you have nonlinearities, and then you have also couplings with different mechanical degrees of freedom. Also, for example, when you're talking about rotations, then you can have already a free particle is coupled in all three rotational degrees of freedom. So I would say that there are many instances where the problem cannot be really reduced to a simple 1D problem. But I think this is the first one of, or let's say one of the first one that I have studied intensively in cavity optomechanics, or well, in levitated optomechanics, that it plays a role, let's say, also such a prominent role, I would say.
Thank you. We're keeping an eye on the YouTube chat as well, and we just have someone say, "Great talk, thank you." So we have some people listening as well.
Ignacio has a question. So.
Okay, please go ahead.
Hello, Marko. Thank you for the nice talk. So you showed this one with two nanoparticles that you want to entangle using the spin. So I imagine you have in mind an NV center, something of that sort.
Yes, yes, yes.
So I had a curiosity. I mean, maybe it's a very stupid question. I've never done these numbers. If you bring this quite close, do you need to worry about the magnetic dipole interaction between these things compared to the gravity if the nanoparticles are like really very light?
So we are thinking also. So I'm working on Sogato on the technical details of this proposal. So as a general comment, there are of course many technical challenges to be overcome, and like prototyping, and probably the final experiment might be slightly different than the one proposed here. But yes, in short, yes, all these effects have to be considered. And as the one you have mentioned, I think it would be important to consider it.
So you want them to be far enough apart or something?
Sorry?
You need them, there is some distance that you need to worry about there, or I guess, yeah, if you have dipolar.
Yes, I think so, but I haven't checked the numbers, so I cannot.
So maybe I will add something here from Marko's point of view. So actually the dipolar over these distances that Marko is talking about, like hundreds of micron, is almost negligible. Yeah.
I see. So it's 100 micron. I see.
Yeah.
So it's quite large distance that you.
Yeah. If there was an electric dipole, it's a problem. It's a magnetic dipole. So you know.
Yeah. So thank you. It would have to come.
All right, so we have one question from the YouTube chat, which says, in the ground state cooling experiment, is there any way to use 3D coupling to further cool below the ground state? Or should the 3D coupling only heat the coolest mode with respect to the 1D case?
Can you repeat the last part? So
yeah, so the last part is, should the 3D coupling only heat the coolest mode with respect to the 1D case? I'm not entirely.
Oh, well,
yeah.
I guess so. I guess it refers to using perhaps other modes to cool even further one single mode, or the opposite would be to use the coolest mode to cool a little bit more the one that are at higher temperature. So this, I guess, definitely the second one, so where you can cool with the one at the lower temperature, effectively the one at the higher temperature. But perhaps there is a scheme also to do the opposite. But I haven't looked into this. It would be quite interesting to find out this. So to cool even further, let's say the mode at the low temperature by exploiting the coupling to one that is at a higher temperature. So destructive interference, again, would be critical to check this.
So
All right.
Before we wrap it up, I guess. So you've explored essentially these for motional degrees of freedom and so the translational motion degrees of freedom and their coupling. Have you started, or have you explored what would happen if you started to, say, couple rotation to translational motion in a useful way? Primarily because rotational motion can inherently be nonlinear. And so any coupling you have with it will be nonlinear and might be an interesting resource for state preparation.
So I have been thinking a bit about what would happen in this setup with rotations. But of course, so there are probably two different regimes. So one would be the regime of vibrations of small oscillations, which is very much like a harmonic oscillator. So a similar analysis that has been done here could be extended also to include vibrations. But you probably have in mind a different regime where the nonlinearities are still present and the couplings between the rotational degrees of freedom would be very strong. That is still on my to-do list, but that is definitely something interesting to see.
Thank you.
Okay, so I can't see any more questions, and the YouTube chat also has no more questions. So I think please, everyone, please thank Marko again. And next week we'll have a talk by Georg Enzian about their experimental systems that they've been working on in Oxford. So thank you so much, Marko. Oh, sorry, we have, is that another question for you, Madassa?
No.
No, okay, so, sorry about that. Okay, so thank you so much, Marko. Please join me in a round of applause.
Thank you.